Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the pyrrole. Pyrrole is a 5-membered ring and how to synthesize pyrrole in the laboratory. Who synthesize this compound in the laboratory first time, so that what are the starting material he has taken and what is the catalyst used for the synthesis of this pyrrole, and after that what are the common reaction shown by that pyrrole. That kind of the discussion we had discussed yesterday. Pyrrole is a 5-membered heterocyclic compound which is an aromatic heterocyclic compound, because we are discussing pyrrole is an aromatic heterocyclic compound, and pyrrole undergoes electrophilic substitution reaction at 2 positions. Why it undergoes only at 2 positions? The reason behind it, we had drawn the resonating structure, and from that we come to know that preferentially we have drawn by considering the electrophilic substitution reaction at 2 position as well as 3 position, and we have drawn the canonical structure or the resonating structure. And what we found that when electrophilic substitution attack at 2 position, there are 3 resonating structures are formed, and finally, and in case of when electrophilic substitution attach at 3 position, there is a less resonating structures are obtained, only 2 are there. And if you compare the resonating structure among these 2 positions, the 2 position resonating structure, in case of the resonating structure, and as we know that as the resonating structure goes on increasing, the stability of that compound goes on increasing, and hence when the electrophile attack at 2 position, that is a most favored position for the electrophilic substitution reaction at that particular position, and therefore the common reaction observed in a 5-membered aromatic heterocyclic compound, especially here we are discussing the pyrrole. So sulfonation we have seen. Pyrrole on sulfonation with SO3 in presence of pyridine gives pyrrole to sulfonic acid. Concentrated H2SO4 cannot be used as a pyrrole undergoes polymerization reaction, and that is the reason why concentrated H2SO4 is not used for the sulfonation of pyrrole. Because if you use as a concentrated sulfuric acid H2SO4, the polymerization occur, means one of the monomer unit attached with another, so that type of the longest chains are formed, complex compound with high molecular weight. So that type of the complication is occur. We cannot stop the reaction at monomer, and therefore concentrated H2SO4 cannot be used. Instead, to get the 2-pyrrole sulfonic acid or pyrrole 2-sulfonic acid, the reagent which is employed are sulfur trioxide in presence of the pyridine, and the resulting compound obtain whatever desired product, whatever we needed product we got over there, or the desired product is obtained by using this particular reagents. So that's the thing we have seen. Now the second reaction which we are going to discuss, that is a freidel oscillation reaction. Second would be the freidel oscillation reaction. Let's see here, freidel oscillation reaction. That the reaction is going to discuss here. What we have looked yesterday, that we already discussed. Second reaction with the freidel oscillation reaction. Freidel oscillation reaction. What is the reagent and how the reaction carried out, that let us see here. Freidel oscillation reaction, pyrrole reacts with acetyl chloride in presence of AlCl3 as a catalyst, gives 2-acetyl pyrrole. Similar to as in case of the furan, we have seen the same reaction will take place, and on the same way pyrrole reacts with acetyl chloride in presence of AlCl3 as a catalyst. The catalyst gives 2-acetyl pyrrole, gives 2-acetyl pyrrole. So that is the compound which we are going to get over here, and this reaction is so simple, freidel oscillation reaction, and this reaction only occur in case of the aromatic compound. And as we know that pyrrole is a aromatic in nature, it is a 5-membered ring, and it is a more aromatic in nature than the benzene, and therefore pyrrole reacts with acetyl chloride in presence of AlCl3 as a catalyst. And as we know that AlCl3, it is a freidel Lewis, this is AlCl3 is a Lewis acid catalyst. And what is the role of catalyst here in general in the organic compound? It speed up the rate of the reaction, and therefore the product is a form with good yield. So that is a speciality of that specific catalyst. Pyrrole reacts with acetyl chloride in presence of AlCl3 as a catalyst, gives 2-acetyl pyrrole. And everybody knows that the structure of pyrrole. The structure of pyrrole I am showing over here. See the structure of pyrrole. As we know that this is a 5-membered ring, and nitrogen has 3 bonds, so 1 hydrogen atom is there, and therefore this is the structure of pyrrole, right? Now when this pyrrole treated with aluminum acetyl chloride CH3 C double bond O Cl in presence of AlCl3, that is a Lewis acid catalyst, this is, which is known as freidel oscillation reaction. Freidel oscillation reaction. And as we know that the pyrrole undergoes electrophilic substitution at 2 position. I am underlying that 2 position. Why 2 position? From the resonating structure we come to know that why 2 position is a preferred one, or the electrophilic substitution occur exclusively at a 2 position if that 2 position and 5 position are vacant. If they are the substituted, we are not going to learn the reaction at T.Y.B.Sc level, substituted furan, only simple plain furan, reaction of the plain furan we are talking. We are not going to talk about the derivatives of that furan or the substituted furan, only the plain furan and whatever the limited reaction we are going to study at T.Y.B.Sc level as far as this level is concerned. Over here, this is a 2 position, as we know that heteroatom getting as a number 1 always over here, and so at a 2 position, 2 or 5 position, both are the identical, so that you can show here at 2 position C double bond O CH3, that is acetyl group is introduced at a 2 position, or that acetyl group is attached at 2 position, and we are getting this product. The name of this product 1 2 3 4 5. So at 2 position 2 acetyl group is there, acetyl pyrrole, 2 acetyl pyrrole, which is the product we have got here. So see carefully how simplest reaction it is. Try to practice to draw the structure frequently. You will be familiar with these structures again and again, and you will be able to predict the product. If in exam what they will give you this starting material and on the arrow this kind of the reagent, and so you have to predict the product. So predict the product is very easy if you know the basic. There is a mechanism also there, because AlCl3 plays an important role here in this particular reaction. It generates the electrophile, means here the AlCl4 minus Lewis base is formed, and here is a electrophile is generated, that is a selenium ion, and that selenium ion generally has a electrophile, and this, as we know, that 5-membered ring which is a nucleophilic in nature. Nucleophile and the electrophile, due to the electrostatic force of attraction between them, and there is a new formation of the bonds are forming over there, carbon-carbon bond. Even though this lone pair present on it, the reaction does not occur on the heteroatom, preferentially due to the resonating structure. The lone pair is involving in the delocalization, and therefore the reaction occur at carbon rather than the heteroatom. So that you should remember while predicting as a product in this particular heterocyclic compound. So that is there. Now let us move on to the next reaction, that is a third reaction which we are going to discuss over here. Similar to the furan, the third reaction will be the, as per as this reaction sequence is considered. First one the sulfonation, second one is the freidel oscillation, and third one generally as the a dizo coupling reaction. Third one is a generally as a dizo coupling reaction. Dizo coupling reaction. Dizo coupling reaction, as we know that benzene diazotized diazonium ion, as we know that when aniline is present, that aniline will be carried out with sodium amide in presence of HCl. The temperature maintained at 0 to 10 degrees centigrade, and the resulting compound form which is a diazonium salt, and that diazonium salt is a versatile in nature, and variety of the organic compound we can prepare, we can made from that diazonium salt, and therefore this diazonium salt, when it is treated with that 5-membered pyrrole, generally the product which you are going to get here is this one. Pyrrole react with benzene diazonium chloride at 5 degrees centigrade gives 2-phenyl azopyrrole. So similar to as a furan, this dizo coupling reaction, pyrrole reacts with benzene. Pyrrole reacts with benzene diazonium chloride. Benzene diazonium chloride at 5 degrees centigrade. At 5 degrees centigrade gives 2-phenyl azopyrrole. That's the reaction generally in the wording we are writing, and now we are going to represent it by showing as a chemical equations. That's the way. Even though you write it, or you can represent only as a reaction and one and the same thing. Pyrrole reacts with benzene diazonium chloride at 5 degrees centigrade gives 2-phenyl azopyrrole. So that is a product which we are going to get over here. Now let us look at, as we know that the starting material or the substrate, everybody knows that this one is a nitrogen having one hydrogen attached to that nitrogen, because nitrogen has 3 bonds. And now this is the structure. The name of this structure is a pyrrole, as we know that. When it is treated with the diazonium salt C6H5, N double bond, N triple bond, Cl, minus charge on chloride and positive charge on the middle nitrogen atom, because it has 4 bond, and this is a dizo coupling reaction. Dizo coupling reaction, and the reaction going to occur at 2 position, and the product you can see here. This is a product here, N double bond N, then C6H5. This is a product which we got over here, and the name of this compound we already have that name written on the blackboard, but for under the reaction, so that you can understood this one very easily. 2-phenyl azopyrrole, that is a name of this compound after addition of that with the treatment with the dizo coupling reaction, resulting products are formed this way, or this is the product which we got over here, and the side product may be as a HCl here in this particular case. H from here, from pyrrole, as we know that 1 H from here, because electrophilic substitution reaction, and you know that substitution reaction means the atom or group of atom removed or replaced from the reactant or the starting material by the other atom or group. That kind of the reaction are generally termed or called as substitution reaction. And here one electrophile, this is a H plus, as we know that electrophile replaces the another electrophile. Strong electrophile replaces the weak electrophile. H plus is a weak electrophile, easily get replaced by this group. The mechanism, generally the mechanism, if you see over here, so let me try to show that mechanism how we are getting over here. So mechanisms are, let me clear this first over here. So I am going to show that mechanism, because mechanism, we know that a detailed study of sequence of steps which are involved in the conversion of reactant into product is known as a mechanism. In the organic chemistry, mechanism is nothing but as a language of organic chemistry. So those are knowing as a language very well, they can express their feeling or whatever message they want to pass, they want to convey to the audience or the people, they can easily convey them. So let us see here the mechanism. Here is a pyrrole, as we know that NH. It is a hydrogen atom. Don't show hydrogen atom here. Here is a N triple bond N, then C6 H5, right? Here is a positive charge over there. Here is a Cl minus already there. And now what is going to happen? This lone pair moving like this, and when this lone pair forming as a double bond here, look at carefully, and after that this double bond is shifted from here to here, and this double bond is going to attack on that nitrogen atom, forming as a bond between carbon and nitrogen, and then there is a positive charge. That positive charge get neutralized by movement of that 1 pi bond is broken, and that lone pair comes on that nitrogen atom, and the resulting product, which we already shown over here, look at here, N double bond N C6H5. When the bond is forming between this carbon and this nitrogen, which is this one, is a new bond formed between heteroatomic bonds are formed, or this is here carbon and the nitrogen bonds are formed, and this is the simplest way to represent that mechanisms over there. So simple. So let us see clearly here, so you don't get confused here. So I will try to show that one. Suppose here what is going to happen? Here the nitrogen atom H. Now when double bond is formed here, and this double bond shifted here to here, now here we can show hydrogen atom here and N double bond N C6H5. Now look at, observe this structure carefully. The nitrogen atom has a 4 bond, 1, 2, 3 and 4. Therefore positive charge comes on it. Now whatever this Cl minus is a conjugate base over here, which is going to abstract that hydrogen atom from here, and then this is going to form double bond over there, and this double bond pushing from here to here, and this double bond again neutralizing that positive charge, and so that the product will be formed. This one, this is the product which I am showing here. Here the double bond, one double bond here, the nitrogen, double bond nitrogen, then C6H5, which is a product which we have seen in our earlier case. That is a final product. The mechanism, those are knowing the mechanism. Arrow pushing shows that is nothing but as a, these are the curly's arrow. He is showing how to show the probable movement of electron, how it can take place. That is a mechanism, and so that we are generally getting as a this type of the product over here. Now let us move on to the next reaction, and next reaction would be, let's see, fourth reaction, which is a Remer-Tymon reaction. Fourth one, which is a Remer-Tymon reaction. Remer-Tymon reaction. Remer-Tymon reaction. And what is it? Remer-Tymon reaction. What would be the reagent, and at what reaction condition maintained there, that we are going to see here. When pyrrole is heated with chloroform and KOH undergo Remer-Timer reaction giving 2-pyrrol carboxyaldehyde. So here when pyrrol is treated with chloroform and potassium hydroxide KOH undergoes Remer-Timon reaction, Remer-Timon reaction giving 2-pyrrol carboxyaldehyde, that is a product which we are going to get, and that reaction is known as a Remer-Timon reaction. If you Remer-Timon reaction, here generally remember CHCl3 in presence of KOH. This is a reagent generally employed and which introduce the formyl group in the aromatic compound. So that is the speciality of this Remer-Timon reaction. Remer-Timer is a scientist name. He discovered this reaction first time, and therefore the name is given to that reaction. Whenever the name reactions are there, so they have a used specific reagent, and that specific reagent generally introduce that specific group into that aromatic compound, and therefore these are the famous reaction, Remer-Timon reaction. Always remember chloroform and the potassium hydroxide generally employed there as an reagent, and formyl group is introduced in the aromatic compound. And as we know that our starting compound is a pyrrol, is already you know that the structure of pyrrol here, right, and it will be treated with CHCl3 in presence of KOH, and this reaction is generally known as Remer-Timon reaction. And the speciality of this reaction, as I already told you, that there is a introduction of formyl group, but formyl group at which position? These two position, that clearly indicate that formyl group should attack at two position. This is known as the CHO. This is a formyl group or the aldehyde group, and therefore the name of this compound is already written over there on the blackboard, but for once again we can write here. This is 1, 2, 3, 4 and 5. At two position formyl group is there, and therefore you can call it as a 2-pyrrol carboxyaldehyde. 2-pyrrol carboxyaldehyde, that is the name of this compound which we got over here. That is a simplest reaction. The mechanism is when this form, that is a carbon chloride is formed, and then they attack at these two position. So here just remember this will introduce as a CHO, because mechanism is not at T.Y.B.Sc level, but whenever it is possible we will see that later on. But here just remember there is a formyl group is introduced at two position, and the resulting product is formed. Now let us move on to the next reaction, that is a hydrogenation. So that is the fifth reaction which we are going to discuss here, that is a hydrogenation reaction. The 5-membered ring generally or the readily they undergoes some common reactions, and those common reactions are, while studying as a furan we have seen furan can show sulfonation reaction, freidel oscillation reaction, dizo coupling reaction, Riemer-Tiemann reaction, then hydrogenation reaction. In addition to that, there are a lot of reactions they have been shown. Wilsmer-Hack reaction, then Gutterman-Koch reaction. These are the different reaction or a Munich reaction. They can be shown by these 5-membered ring, but as far as T.Y.B.Sc level is concerned, we will see some frequently or the commonly occurred heterocyclic compound that we are discussing over here. Now the fourth reaction, I think this is a fifth one. Fifth reaction will be this one. Fifth one is a hydrogenation. And as we know that hydrogenation, it is a process of addition of molecular hydrogen across the carbon-carbon multiple bond, and it get converted into as a saturated compound at the end product is there. So similarly here hydrogenation reaction also shown by this pyrrole on catalytic hydrogenation at 200 to 250 degrees centigrade gives pyrrolidine. So that is a so simple reaction. Pyrrole on catalytic hydrogenation pyrrole on catalytic hydrogenation at 200 to 250 degrees centigrade gives pyrrolidine, that is a saturated heterocyclic compound which is belonging to as a non-aromatic heterocyclic compound, pyrrolidine. And as we know that here this is a structure which I am showing here is a pyrrole, right? This is a starting compound now. Pyrrole, when it is treated with the catalyst generally used here H2 in presence of Raney nickel, the temperature is around 200 to 250 degrees centigrade. The product will be formed is this one. The product which we are going to get here is this one. This is a pyrrolidine. So pyrrolidine. And the one question may appear here, this is the aromatic compound, as we know that because we fulfill the aromatic criteria, but this is a non-aromatic heterocyclic compound. If you talk about another difference between these about the basicity in terms of the organic chemistry, one statement is generally made: those organic compounds containing nitrogen atom are basic in nature. Here both the structure, one pyrrole as well as pyrrolidine, both having as a nitrogen atom, and they should show the basic property, but here pyrrole does not show as a basic property, whereas pyrrolidine is a more basic in nature. The reason behind it, why pyrrole do not shows basic property, even though it contain as a nitrogen atom, whatever the lone pair present on that nitrogen atom, in this particular case that nitrogen atom are involved in a delocalization to complete the sextet according to as a Huckel's rule, which should fulfill 4n plus 2 pi electron fully cyclic, planar, fully conjugated system containing 4n plus 2 pi electron system are known as a aromatic compound, and therefore these lone pair which are present on the nitrogen atom in pyrrole, they are not free. But if you see here, if you observe the structure pyrrolidine carefully, the lone pair which are present on nitrogen atom, they are readily available for donation according to the Lewis acid base theory, which can act as an base. In addition to this, the ring residue alkyl group here, which is a electron releasing group, which gives the electron density to the nitrogen atom. Already nitrogen has a lone pair. Along with that, again methyl group also providing, also giving electron density to that nitrogen, and the rate of donation of that lone pair is tremendously increased in that particular structure, and therefore pyrrolidine is a more basic in nature than the pyrrole. Pyrrole does not show basicity at all because it is an aromatic compound, whereas pyrrolidine is a basic in nature, it is a strong base. I think whatever the important reaction regarding that pyrrole we have seen over here. In next lecture we will discuss about the thiophene, how thiophene can be prepared, can be synthesized in the laboratory, which is a method adopted for the synthesis of that pyrrole that we will see in our upcoming lecture. Till then, have a nice day. Thank you.